at later, and 2, so everybody can see it equally. So if my middle monitor were working, that would help, but that's the way it goes. So we're talking about this idea in the Frozen Planet video. That's orange, and that may not be the best color to use. Of brinicles, like icicles. So what is brine? What is brine?
Is that the frozen water that's going down?
It has to do with the frozen water, but that's not what it is. Okay, anybody have a different idea of what brine is? You ever heard of brine shrimp? Yeah? No? Maybe? Have you ever heard of brining cucumbers to make pickles? Okay, well, clearly my realm of influence is expanding. So brine is very salty water. Basically, that's what brine is. All right, so you already knew that seawater, such as what we were looking at in the video, is salt in water, right? Seawater is salty. We all knew that. But what happens when you lower the temperature and the water starts to freeze? What happens to all that salt? So we had the brinicles coming down. Did you notice that there were kind of streams running through the water that you could see, like you can see heat waves coming off a road in the middle of summertime? What you were seeing was in those streams was the brine. And so what's happening is as water gets added to the ice, that leaves the salt behind in the remaining water, but it's more concentrated. Does that make sense to everybody? We're kind of extracting the water from the seawater. We're taking the water molecules out and throwing them into the ice crystals that are forming, and then that just makes the salt water more concentrated. Does that make sense? Questions about that? Okay, so back to the idea of density and temperature. Water has a certain density. And because water is our standard of measure, the density of water is 1. We just sort of arbitrarily say water has a density of 1. So anything with a density greater than 1 is more dense. And what is something that's more dense going to do when it's suspended in a liquid that's less dense? What does the more dense thing do? It sinks. So what you saw was the icicle forming and then the brine sort of streaming away from it down because of density. Does everybody understand how important the density is? Okay, so what happens then below that, so if this is the sea floor, so this is where the poor little starfish are sitting that are going to go frozen if they don't move, all that brine starts sinking down. And because it's denser than the rest of the salt water, it can actually kind of sink down into the sand. And remember, we're talking about the bottom of the ocean around Antarctica, and it's pretty, I mean, even where they were scuba diving, which that's a trip, it wasn't that deep. It's still deep enough that the pressure alone kind of forces that denser brine down into the ocean. But what happens next has to do with the temperature. So the other aspect of temperature is the freezing point. What's the freezing temperature, the freezing point of water? Water freezes at what? I'm not hearing loud answers. So let's do it in Fahrenheit and Celsius. 32. Now, in science, we don't usually use Fahrenheit. We use Celsius, or we can call it centigrade, but it's usually called Celsius. Does anybody know the freezing temperature of water? It's arbitrarily set at 0. 0 degrees Celsius is defined as the temperature at which water freezes. Okay, and does anybody know the opposite of that, the temperature at which water boils in Celsius? No, that's Fahrenheit. Very good. What about in Celsius? It's 100. And that was just sort of the guy that devised that scale, whose name was Celsius. Figured, just set it that way arbitrarily. I'm just going to say whatever temperature it is that water freezes at, that's 0. And whatever temperature water boils at, that's 100. And then he made his thermometer sort of evenly graded between. Are you with me on that idea? Okay, well, the problem is that's for pure water. What about salt water? Seawater. Yep. Seawater has salt in the water. It has other things too, but we're totally ignoring everything except the salt. Has a lower freezing point. Again, this is a physical property, not a chemical property. So if it has a lower freezing point, then if plain water is at 0, is it going to freeze if it's salt water? It doesn't freeze yet. Okay? And the more salt there is, the colder it can get without freezing. So as the water crystallizes into ice in those ice fingers, the surrounding water has more and more and more salt in it, and it can get colder and colder without freezing. Okay, we call that supercooled. Okay, so what happens down there at the seafloor? We've got this brinacle that's grown down and is growing this ice finger of death, and our poor little starfish are all caught up in that because they don't move very fast. But in the surrounding area, you've got this brine, and it is pressurized and it's salty concentrated, so it's super cooled. But as the water comes in contact with this brine along the seafloor, it too will start to form ice crystals. Unrelated to the ice finger you get along the seafloor, you just get water freezing into plates of ice, just sitting right there on the ocean floor. Okay? Because it's in contact with that supercooled brine, which is under very high pressure. So any water molecules that find each other are going to start to form ice crystals, and then it's just going to grow. Okay, now tell me what you know about ice and water in terms of density. Which one is denser, liquid water or ice? Remember that the denser thing sinks, which means the lighter thing floats, right? So which one floats on top of the other? Ice, everybody knows ice floats. Okay, so tell me what's going to happen to these plates of ice as they form. They're going to start floating up, taking with them any starfish or other little things that got frozen in them. They float and they embed themselves on the top of the ice cap on the top of the ocean. All that's happening right now. Okay, so if you went to Antarctica right now and you looked out from the ship that you're on, all you would see is pretty much a frozen sea. Okay, but what's happening underneath? All these ice fingers are forming, these ice plates are forming on the seabed and floating up. And all of that is simply due to the properties of water, particularly the properties of water mixed with brine. Okay? So, any questions remaining about that? All right. Let's see if I can figure out how I want to go back to here. There we go. All right, so we're going to talk about why water is the way it is. And as I retool, I know some of you just came in, so if you came in after I handed out your periodic tables, you're going to want those back. Melissa's still not here. Brandon Bonfanti, Trevor Hodge, Crystal de la Garza, Jadarius Carroll, Mercedes Williams, Trevor Johnson, Julie Godwin, Maxwell Lee, All right, so now we're going to look more at the chemistry of water. We understand this concept of how density and temperature and salinity are all going to affect the way water behaves physically, and you can see that that has an impact on biological organisms, but we need to have a better understanding of why water is the way it is. And we talked last time about covalent bonding, right? So if we just recall what we said about that, then we know that carbon makes 4 bonds, right? Nitrogen makes 3 bonds, oxygen makes 2 bonds. And if we bond these with just hydrogen, we did this last time, didn't we? Yes? Yeah. Okay. So we can make methane, we can make ammonia, and we can make water. All right? So what we're going to focus on today is the idea of the lack of balance in these molecules. And so as we try to take a look at that, let's just redraw them a little bit smaller. If this is methane, would everybody agree that wherever there's a hydrogen on one side of the carbon, there's a hydrogen to balance it on the other side? Would you agree that's a symmetrical molecule? Whereas when we draw ammonia, what would you say about that? It's kind of unbalanced. There's like a missing corner. And what about for water? It's definitely tipped to one side, right? When you remember how the electrons are found in the valence shell, with carbon, if we just draw the valence electrons, there are 4 of them, right? This was the whole point of drawing this, and this is why I made a point of giving you your papers back so you could look at them. With nitrogen, what did we have in our valence level? Not 4, but 5. Well, let me change that just a little bit to make it match. And what about for oxygen? How many valence electrons does oxygen have? What column is it in? On the periodic table, what's the column of oxygen? 6. So how many electrons does it have in the valence level? 6. So I've got 4 drawn. I'm going to draw 2 more. 5, 6. So with that in mind, then, when we're looking at adding in the hydrogens, then the hydrogens have to contribute the missing valence electrons. Remember, they're going to share them, and that's why we call it covalent. So for methane, each one of carbon's 4 valence electrons needs a partner. But for nitrogen, only 3 of them need a partner. And of course, for oxygen, only 2 of them. And so what that means in terms of the way the atom behaves is that for nitrogen, I have here this pair of electrons that belongs completely to nitrogen and isn't shared with another atom. And for oxygen, not 1 pair, but 2 pairs. Okay, so they have their own electrons, and of course electrons have what kind of a charge, positive or negative? Negative charge. So that means that these little negative guys over here are not capped or covered or connected to a positively charged hydrogen nucleus. Are you with me on that idea? So that makes anywhere that you have an unbonded pair of electrons, it makes it a little bit negative. And the sheer size of these atomic nuclei tends to make them electron hogs. We say they're electronegative. They attract the electrons more strongly than the little hydrogens do. And consequently, the electrons that were donated by the hydrogens, in fact, are being sort of pulled more strongly by the bigger partner, nitrogen or oxygen. And the result of that is that the hydrogens become just a little bit positive. Does everybody see why that would be? Any questions about that? So it's kind of like they're playing tug-of-war, and the nitrogen or the oxygen is bigger and stronger and can pull more strongly. Okay? Everybody got that concept? All right, so then if we look at the molecules, and if we draw them in what we call a space-filling model, then here is the carbon atom. And then what about the hydrogen atoms? They kind of sit symmetrically on each side. Okay, so if this is the nitrogen atom, then how many little hydrogens do I get? If that's nitrogen, how many hydrogens am I going to add? 3, because NH3 is ammonia, so I've got 3 of them here, one here, and one here. These are not entirely drawn to scale. And so if it's oxygen, then here's my oxygen atom. And then how many hydrogens do I get? Just 2. And they sit kind of lopsided. And to explain that to you, it helps to have 3-dimensional models, and I just happen to have some. So we're going to play with the models for a little while. I'm going to ask you not to steal my toy. And I only have 6 of these. They're very expensive, so every 2 tables is going to explode. For y'all. So be nice and share. And what you need to be able to do is to explore the properties of the little models. I had one class yesterday that, I don't know how many times they dropped their pieces. I was actually kind of going to tell them not to play with them anymore. So remember, you have to share with the other table. And the first thing I want you to be able to do is to identify what this thing is. So if you're not getting your share, then scoot your chairs to the table that has the clip. Where is my little note? It tells me what everything is. Well, that's not what I wanted to show. All right, so what are these guys? These are water molecules. Red oxygen, white for, where is my auto zoom? White for hydrogen. Okay, so these have magnets in them, clearly. Can you figure out how they stick to each other? Is there a pattern to how they stick to each other?
Yes, has to touch a white.
Okay, so if you tried to force a red to a red, what would happen? They repel each other, okay? And white repel each other. So this is our model of how the atoms actually behave. So I'm just going to kind of park a picture up here on the board. If this is the oxygen, and it's got covalent bonds to 2 hydrogens, then remind me who's positive and who's negative. Hydrogens tend to be a little bit positive, oxygen a little bit negative, and you know that opposite electrical charges attract each other. So if we tried to put another water molecule right here, which part of that water molecule would be attracted to these hydrogens? If this is a hydrogen, it's the oxygen that's attracted, right? And the hydrogens are repelled, so they're going to move as far away from the other hydrogens as they can. And so what we get here is a little bit of an electrical attraction between the two, And this is classified as a chemical bond. It's a very weak chemical bond, and it's not a bond inside of the molecule, it's a bond between two different molecules. And that is a hydrogen bond. And you need to be able to contrast that to the bond between the oxygen and the hydrogen within the molecule. That is called a polar covalent bond. Did we talk about polar bonds last time? I'm pretty sure I don't remember doing it. So I want to make sure I explain why it's called that. It's called that because it has poles. So each water molecule has poles. What are the poles on a water molecule? If I just have one molecule, what are its poles? The oxygen and the end where the two hydrogens are form the opposite pole. So just like the Earth has a north pole and a south pole, and magnets have north and south poles, so do these water molecules have poles. We don't call them north and south. What do you want to call them? How about positive and negative? Okay, so water is a polar molecule, and each bond that is found between the oxygen and the hydrogen is a polar bond. Everybody okay with that basic concept? Questions about that? Okay, so where are our polar bonds? Which bonds are polar? When you look again at our figure, as soon as it pops up, remember that we said that in methane that it's completely symmetrical, right? Whereas in ammonia, we have this one little pair of electrons here that's not shared, so that's a little bit negative, and the hydrogens here are a little bit positive. And with water, we have two pairs of electrons that are not shared, so that's even more negative, and that's more positive. Okay? So we need to have an idea, the ability to predict when bonds are going to create this little bit of electrical charge and when they're not. And so we're going to have a list of things that have polar covalent bonds and everybody else. And the term we're going to use for anything that does not form polar bonds is very straightforward. We just call them nonpolar. All right, so referring back to our, oh crap, I did it again. I keep hitting the wrong button. So referring back to our list, we had methane, we had ammonia, and we had water. The bond here was a bond between carbon and hydrogen. The bond here is between nitrogen and hydrogen. The bond here is between oxygen and hydrogen. Which ones of these are polar? Which ones are a little bit negative on one side and a little bit positive on the other side? OH is polar. NH is polar. What about CH? Definitely nonpolar. So that's the start of our list. Now, before we finish playing with our toys, what else do you have in your kit besides water? Does everybody have a little blue sphere and a little green sphere? Yeah? And do you have something that's gray? At least one thing that's gray. And maybe in two pieces, but this is what it should look like. Okay, so find your gray piece and tell me whether it's attracted to the water or not, the water molecule. Yes or no? Everybody agree no? So we know that water has polar bonds, and we know that carbon and hydrogen have nonpolar bonds, and in fact the gray is a carbon atom. And we already know that the white is hydrogen atoms. So how well do things built of just carbon and hydrogen mix with water? How well do they mix with water? They're not attracted at all, right? So things that are built just of carbon and hydrogen are nonpolar, and therefore they don't interact well with water. Water loves things that have electrical charges because water has electrical charges. Okay? Are you with me on that? So back to our list. Anything that is nonpolar are things that don't interact well with water. Carbon and hydrogen, carbon and carbon are on our list so far. Okay? They do not interact well with water. What's on our polar list? OH and NH. Okay? Now, I don't want to neglect the fact that there are things that don't form polar bonds at all, or don't form covalent bonds at all. Those are our ions. So what you have in the little green sphere and the little blue sphere, those are ions. Okay? And what I want you to be able to tell me right now, first of all, you can tell me that the blue is smaller than the green, right? Okay, which one is positively charged and which one is negatively charged? Figure that out at your tables. Which one's positive, which one's negative? Is there anybody that can't figure that out? All right, so which one's positive, which one's negative? The blue one is? What? Positive. How do you know? Which end of the water molecule is the blue one attracted to? The negative oxygen. That's a stronger attraction. Will it bind to the hydrogen? Yeah, it doesn't like to. So because the blue one is attracted to the oxygen of the water, and we know that the oxygen is the negative part of the water, then in order to be attracted to the negative oxygen, it must be positive. Okay, whereas the green one likes to bond to the hydrogen of the water. We know the hydrogen is positive, therefore the green one is negative. These are models of sodium fluoride ions. This is salt. Okay? Does everybody see how we figured out what we know from our models? Questions about that? All right, just to avoid the temptation of starting to play games, would you please pack them back up? That way you can get them packed back in the can. One of the things that on your test I'll be expecting you to be able to do is to recognize polar and nonpolar bonds and be able to predict whether that something is going to mix well with water or not. Things that are polar or ionic mix well with water, and things that are nonpolar don't. The good news is that's the end of our polar list. Those are the only two things I'm going to ask you to recognize as polar for now. We may add one. I haven't decided how important it is. There's one more we might add later. So if those are the only two polar bonds, then everything else that we're going to study is going to be mostly nonpolar. And you're thinking, oh, well, good, that's a short list. But in fact, there are lots of molecules, and next week we'll start with our organic chemistry. There are lots of molecules that have those polar bonds in them. So I'm going to draw the structure of glucose, sort of, and I'm going to ask you to copy what I draw on your page that you're going to turn in. This is 6 carbons in a chain. And after you've copied it, then I want you to label all the polar bonds and the nonpolar bonds. There's not going to be any points lost if you don't draw it accurately, but there it is as well as I can get it up there.
For polar, do you just like put like a P next to it?
What?
Or are we looking for non-polar or polar?
You're labeling both. So you can use P for polar and N for nonpolar. So if you need a little more direction, then let's start with the bond between carbon and another carbon. Is that polar or nonpolar? You have your list right there, right? So that's nonpolar. Any bond between carbon and another carbon is nonpolar. Okay, so see what you can do with the rest of them. This is to turn in, so make sure your name, your table number, and today's date, which is September 1st. Oh, and that reminds me, I'm supposed to check your IDs today. So while I walk around, will you please show me that you have a gold sticker or come up with a good reason that you don't? All right, so for those of you, and there's more than one, that don't have their IDs today, if you run into one of our ambassadors who has the gold vest, the guys walking around, ask them for a day pass. Okay, that'll keep you out of trouble for today. All right, so what else is not, what's on our non-polar list besides carbon to carbon bonds? Carbon to hydrogen bonds, so we can mark all of those. There's a lot of them, aren't there? What about the carbon to oxygen bond? You know, it depends. And I misspoke when you asked me that. This guy right here is double bonded. And that's the one I was dithering about whether to bother to tell you about, and then I went ahead and drew it. That's actually polar. It's a little bit polar. This one's polar. I'll probably never test you on that, but just file it away. Someday it'll come in handy to know that that's polar. But the other ones are single bonds, and because carbon and oxygen are about the same size as each other, in that tug of war between electrons, nobody wins, which means nonpolar, okay? So all these bonds between, the single bonds between each carbon and its oxygen, those are all nonpolar. So in terms of just inventory, who's winning between polar and nonpolar? It seems like it's mostly nonpolar. So let's go ahead and mark our polar bonds. Which ones are they? The ones between the oxygen and hydrogen, how many of those are there? 1, 2, 3, 4, 5. There's 6 oxygens, but the 6th oxygen is double bonded, and it's a little bit polar. So if I just asked you which bond type there's more of, polar or nonpolar, what's your answer? Nonpolar. Now, if I asked you to characterize this molecule, is the molecule polar or nonpolar? Your first inclination is probably to say, well, there's more nonpolar than polar, and you'd be wrong. So I don't like to trick you, so I won't do that. But there are enough polar bonds in this molecule to make that puppy polar. Okay, that's a polar molecule. It has enough OH bonds on it that it behaves well with water. This is, I already told you, this is a molecule of sugar. That's a glucose molecule. Does sugar mix with water? Why, yes, it does. So anything that mixes well with water that you already know mixes well with water has got to be either polar or it's ionic. And as we explored in our little kit, salts are ions. So does salt mix well with water? Yeah, of course it does. It's ionic. And that means it has electrical charges, and since water has electrical charges, that means it mixes well. Is that all right with everybody? Questions about that? Okay, so starting next week, we're going to be building these more complex molecules and exploring their properties. And the main property is going to be, does it mix well with water or not? Okay, so can you name something that does not mix well with water? Oil, gasoline. Okay, so are they built mostly of polar molecules or mostly of nonpolar? Nonpolar, and next week we'll see why. Okay, so in biology, we actually have 4 classes of organic molecules that we care about at the freshman level. We have carbohydrates, which include sugars. We have lipids, which include fats. We have proteins, and we have nucleic acids, the DNA and RNA associated with the nucleus of a cell. Of those 4 categories, which one is pretty much nonpolar? Carbohydrates, lipids, proteins, nucleic acids. Which one included fats and oils? Lipids. And that is the overriding characteristic of the lipid category, is that they're built mostly of nonpolar bonds and they don't mix with water very well. They may not have much of anything else in common, but that's their defining characteristic. They don't mix well with water. That's how important it is. Okay, so the first question we would ask of any chemical in this class is, does it like water or not? That's going to be like, if you were asking 20 questions, that would always be question 1. Okay? Does everybody understand how important it is that the chemical structure of water is that it's composed of polar covalent bonds? And can you name something else besides OH that is a polar bond? What's the other one? NH. And our third one, if we want to press the point, is carbon double bonded to oxygen. You should probably just go ahead, let's just give up and put it on our list. Actually, stop. Let's rewind so that the oxygen is on the same side. of the molecule. The oxygen here, the carbon there. And to fill out our list, anything bonded to itself is symmetrical, right? In a tug-of-war, there are no winners. That makes it nonpolar. So oxygen to oxygen, nitrogen to nitrogen. Nitrogen to carbon, oxygen single bonded to carbon, and any other molecule that is just an atom bonded to another atom of the same element is going to be nonpolar, okay? And then to round out our list of nonpolar, and I'm kind of out of room, this one is kind of different, so let's make a point of it. This is carbon dioxide. Right here is a glitch in my program, but it's nitrogen single bonded to nitrogen. I don't think we're going to see that, so not too worried about it. Okay, so what was this guy right here? What's that? That's carbon dioxide, CO2. Polar or nonpolar? I got it on the nonpolar side. Okay, it's symmetrical, right? There's two oxygens exactly opposite each other fighting over the carbon. Nobody wins that tug-of-war. Okay? And then what is this guy right here? That's oxygen gas. So are oxygen and CO2 important to us biologically? You betcha. And you need to know that they're both nonpolar. Okay? Questions at this point? All right, so water has a lot of other unique properties, and for the most part, I'm going to ask you to refer to your textbook on those. But when you do, I want to make sure that you have some sense of that polarity of water, that idea that there are polar covalent bonds, that makes sense of most of it. So even in explaining why liquid water is denser than ice, it comes down to understanding the polar bonds. So when water is in its liquid form, the molecules are moving and they can actually compress a little bit closer. When water forms ice, it forms a crystalline structure that has the molecules spaced a little bit further apart. And it's because of the hydrogen bondings of the water molecule that the crystalline structure of ice is less dense than the liquid form of water. This is very unusual. Most things are denser in their solid form. The solid packs the molecules together. So if you took dry ice, does anybody know what dry ice is? What's dry ice made of? It's carbon dioxide, actually. It's liquid. It's frozen CO2. Please don't play with that stuff at home. It really will freeze your fingers. Don't inhale the fumes. It's carbon dioxide. Let's don't. But if you could play with it in a lab where you could take it from its normal gaseous state to a liquid state to the frozen dry ice state, then you would find that that dry ice sinks in liquid carbon dioxide. Frozen nitrogen sinks in liquid nitrogen. Liquid hydrogen, same thing. Anything in a liquid versus a solid form, the solid is denser. What's the most notable exception to that? Water. In water, you already knew ice floats. What you may not have realized is how unusual that is. And then the impact of that is actually mind-boggling. So imagine that you were fishing on a pond. So here's a pond. Let's put some fish in it so that you can have some success in your fishing expedition. So get some colors in here. So there's some fish down there, and you're fishing. You like to fish. Fine. In Texas, no problems, right? Go to Iowa in December or January. What do you have to do before you can fish? You have to break through the ice, right? Okay, so you break through the ice, and then you can continue to fish. In the winter, the air is colder than the water. The water temperature is actually higher than the air temperature. Again, that has to do with the properties of water. Water, because of those hydrogen bonds, can absorb more heat than air, which is gaseous. So it stays warmer. So when the cold fronts come through and the air hits the water that freezes first is the surface water, right? Because the air's colder than the water. If ice sank, if ice were denser than water, then what would happen when the ice formed on the top?
All the water be pushed out.
Well, the ice would just sink. Okay, and then what would that do on the surface then? If the ice sinks, you've got more liquid water exposed on the surface, it's going to freeze and sink. And then as that occurs, these ponds would freeze from bottom to top. They'd freeze at the top, the ice would sink, they'd freeze from bottom to top. What happens to these fish? Yeah, they're frozen just like the starfish and the barnacles. Okay? But that's not, in fact, what happens. Because ice floats, the ice can form on the surface and stay there, and in the process it forms sort of a blanket that protects the liquid water underneath from that very cold air that would cause it to freeze. So ice insulates the liquid water underneath, keeping the water deep in the pond liquid all winter long and letting the fish keep swimming around. So everybody see how crucial that is? If it weren't that way, then our oceans would be frozen, and we would not be here to talk about it. Does everybody understand how crucial it is that ice floats? If you want to believe in miracles, that's one I'm willing to buy. It's miraculous to me that ice floats, because if it didn't, we wouldn't be here. Plain and simple. Okay? Questions about that? Can these ponds freeze all the way to the bottom? Can they? In Iowa, you bet they can. Okay? It can get that cold, but not all of them do, and the rivers tend to flow. Okay, so consult your textbook, read the questions. By the way, I want to remind you that I have a Test 1 review posted in Canvas. Some of you guys have not logged into Canvas yet at all. You're going to want to do that no later than this weekend. I also have posted some videos to help you get through your understanding of basic chemistry. They're all in the Chapter 2 resources page. So be sure you look through that. I also have a link to the Brinicle video if you want to watch it again. But I'm assigning you specifically to finish up on the properties of water. Okay? So we have one topic left to discuss, and that's the idea of acids and bases. And for now, what I want you to have is more or less just a basic understanding of when we talk about acids, bases, and pH, that you're familiar enough with the terms that if I ask you for definitions or descriptions or ask you to read a pH scale and tell me what it means, that you'd be okay with that. The applications of this are going to be coming way down the road, okay? But you need to have an understanding of the basic concept of acids and bases. So we use pH as our measure. Is there anybody in here who's never heard of pH before? All right. So pH is the measure of the hydrogen, and again, we use water as our standard. Why do we use water as our standard? That's what we're made of. That's the most common liquid component of life on Earth. So we say water is neutral, and when we measure the pH of water at room temperature, it turns out to be 7. Okay, so it's not, by definition, 7 is neutral. It's the same as we did with the temperature scale. We set 0 as the freezing point, 100 as the boiling point, and just kind of made the scale in between. What we did with a pH scale was measure the pH scale of pure water and determine that that's neutral. All right, the chemistry behind that is a little bit more complicated. Before we get into it, let's get some definitions. So when you look at what it means to be an acid, it means that If you have a lower pH, you have more hydrogens. To me, this is intuitively backwards. I want lower to mean less and higher to mean more. And I'm going to talk to you about the math behind that, but if you're like over my head, just learn the definitions for now and the rest will come eventually. Okay? So I think the thing to remember is if you add acid, which way does the pH go? Down. If you add acid, pH goes down. If you can remember that, then you can figure out the rest, I think. Okay? You add acid to a solution, the pH goes down. All right, but remember that pH is a measure of how many hydrogens there are. So let's figure out why that is. It's not just the hydrogens that are bonded in a molecule. So if this is a molecule of water, do we count those hydrogens in our measure of pH? It's only ionic. It's hydrogen ions that we count. Hydrogen ions are counted in pH, not hydrogens that are bonded. So that means they have to ionize or dissociate. That means they have to break loose. Does that happen to water? And it turns out that yes, it does. A very tiny amount of water molecules will actually break one of the bonds and separate off a hydrogen ion. Water does that. Not a lot of it, but a little bit. Okay, so far? So it's kind of like that's a polar covalent bond that decided it wanted to be an ionic bond and it just broke loose. It just does that. How much does that? Not a whole heck of a lot. So if I take 1 liter of pure water at room temperature and measure, here's my beaker of pure water, and I measure in that how many hydrogen ions there are, that is how many molecules of water actually broke a bond, the number is vanishingly small. How many zeros up there after the decimal? 6 of them. That's kind of a pain to write, so we're going to write it in scientific notation. 0.00000001. Let's count how many times we have to move that decimal to get it to be 1. 1, 2, 3, 4, 5, 6, 7. So I write that as 10 to the negative 7. That's scientific notation converted to exponents. Everybody okay with that? You probably learned it in chemistry in high school. You might have vague memories of having learned it and then promptly forgotten it. So just trying to refresh your memory. All right, so does everybody see the 7 up there? That's where the pH number comes from. Okay, that's pure water at room temperature. That's the concentration in terms of the number of molecules that actually broke their bonds. So that's the count of, and we use brackets to indicate concentration, the concentration of hydrogen ions. And so nobody wants to write all those exponents, so we just grab that number. That's where the 7 comes from. And that's the part that if you didn't follow that explanation, don't freak out, okay? Just remember that it's 7. All right, but in the process of doing that, when I take a water molecule, even a small number of them, and I break the bond, what else do I get besides a hydrogen ion? I get this other part, which is the rest of the molecule, and it has a negative charge. And this is called a hydroxyl, and it's the second anion on your list to learn. What was the first anion I gave you to learn? Look back through your notes when we did the periodic table and we were learning which things form cations and which things form anions. Hydrogen's a cation, positive charge. Which one did I teach you has a negative charge, an anion with a negative charge? Okay, so looking at the periodic table, which I handed back to you so you'd have it for reference. If the cations are on the far left of the periodic table, where do you look for the anions? Not on the far right, because that's the inert guys, but the next column over. So who's in column 7? Chloride. Chlorine is the element, chloride is the ion. All right, so chloride ion is the first anion I gave you to learn. This is the second one. Okay? And because of the way ions attract, I can make a bond between hydrogen and chloride, right? Or sodium and chloride. But I can do the same with hydroxyl. So I can make a bond between hydrogen and hydroxyl. Of course, that's just water. But can I make sodium hydroxide? Can I do that chemically, hypothetically? I sure can. That, folks, is lye. And we use lye to clean plumbing. Plumber's helper, that's what it is. And they'll actually sell it in pellet form. It's really greasy. It's extremely powerful stuff. Please do not play with this stuff at home. Okay, but lye is sodium hydroxide. And it's extremely reactive with water. What happens when I put sodium hydroxide in water? If I take my lye pellets, sodium hydroxide, and I dump it in water. We know water molecules attract ions. We played with that in our kits, right? So the sodium gets pulled off by the oxygen of the water molecule, right? Gets attracted to the water, and that leaves all these OHs out there. And the thing about OHs is they're very, very good at pulling in any loose hydrogens. So did I have a lot of loose hydrogens in water? Not a lot, but I had some, and now my lye, my hydroxyl ion, is going to suck them up. And that's going to reduce the amount of free hydrogen ions that I have in solution. And the lower that number is, the higher the pH is. Okay? So that was a logical progression, but if you're thinking this is all too much too new to me, let's just go through some basics. If I take hydrochloric acid and I put that in water, it's going to split the ionic bonds. They're going to dissociate, we say. It dissociates. Dissociate means the ionic bonds break. What just happened to the amount of hydrogen ion, my concentration of hydrogen ion, when I added this acid to water? Did it go up or down? Goes up. I just added more. And look back through what you wrote down. Does that make the pH go up or down? Makes the pH go down. Okay, so if you need a moment, write that down. So you'll have it to refer to. Put it in your own notes, not in what you're turning in. If I put acid in water, it dissociates. That means more loose hydrogen ions. And the more loose hydrogen ions there are, the lower the pH. So adding acid lowers pH. Okay? Let's do the opposite. You ready? What if I take sodium hydroxide and put that in water? What do I get when it dissociates? What two ions do I get? Sodium ion separates from the hydroxyl ion. When I'm measuring pH, I don't care about the sodium. I'm just worried about the hydrogens. So this is a two-step process when we add these things that we call bases. So the hydroxyl ion then reacts with the available hydrogen ion to form more water molecules. So what happens to the concentration of hydrogen ions? It's going to go down. And what does that do to pH? Makes it go up. Okay? So if I add acid, what happens to the pH? Goes down. And if I add base, it goes up. If you can remember at least those 2 points, and they're the opposite of each other, so if you remember one, can't you remember the other? Then you have a start to figuring out just about anything else. Okay? So far? Questions at this point? All right, there's another nuance we need, and that is the difference between a strong and a weak acid or base. And this is all relative, so some are weaker than others. And I'm never going to ask you to figure out how weak a weak acid is, but I'm going to give you a list of acids to learn. Okay? So acids and bases, strong acid, hydrochloric acid. Strong bases include anything with hydroxyl. It can be sodium hydroxide, it can be potassium hydroxide, anything with OH is strong. Okay? I'm going to give you the name of a weak acid and its corresponding weak base, and then I'm going to draw a picture. So the acid I want you to know is carbonic acid, and the base that goes with it is bicarbonate. Carbonic acid and bicarbonate. Have I got the names written down? All right. The difference between strong and weak. If it's strong and I put it in water, every molecule dissociates. There's not a single molecule of the original stuff I put in there left. But if it's weak, it doesn't all dissociate. So draw this picture in your notes. This is carbonic acid. It's an acid. What does it need to do? What do all acids do? That makes them an acid is that they don't dissociate and give off a hydrogen ion. These two, it's got 2 hydrogen ions. It really doesn't matter which one it gives up. It's just going to give up one of them. And here's that little loose hydrogen ion. What makes this weak is that some of the carbonic acid will dissociate, but some of the bicarbonate will take its hydrogen back again. And we indicate that in chemistry and biology by drawing a double arrow. So if I put 1,000 molecules of carbonic acid in some water, how many of those 1,000 would dissociate? All of them or less than all of them? Less than all of them. In fact, about half, close to half. And in chemistry, we actually measure exactly how much, and we measure the strengths of acids accordingly. For us in here, we don't really care about that. Okay, does everybody understand the chemical basis behind acids, bases, pH, weak, and strong? Okay, we're about out of time. By next Tuesday, you should be finished reading, reviewing, and studying Chapter 2, and ready to start Chapter 3. As always, if you will, make sure your name, date, table number are on the sheet of paper you're leaving for me. Stack them in the middle of your table. Pick up your trash. And make sure you take all your belongings with you on your way out the door.